All right, hello everyone, and thank you for joining us for this installment of our Tech Tuesday series. Today we're going to be looking at the state of the 3D scanning industry as a whole. But first, I want to give you just a quick background on me and CamLogic. CamLogic has been around for the better part of 2 decades, and if you can't tell from the name, we started in the CAM industry. We've now expanded into many other facets of engineering and production, including 3D scanning, of course, CAD, CAE, and 3D printing. And because we started toward the end of the production process and worked our way to the beginning, we have the fundamental understanding of what has to be done to assure that each step of the production process will result in a product that will actually work or fit into the next phase of development. But so here's what CamLogic is really all about. If you're asking me, we are a Siemens PLM partner, so we offer training and support for NX, NX CAM, Solid Edge, and Team Center. We also have a staff dedicated to 3D scanning and, of course, 3D printing, both of which encompass hardware sales and services. And because we have engineers, sales, and support staff dedicated to these 3 facets of engineering, we have the knowledge and perhaps more importantly the experience to show you how to tie all these tools together so that you can be better designers and engineers. So I like to think of CamLogic as the glue that ties these 3 bodies of knowledge together into one amazing resource for designers and engineers. As for me, just a quick background, I manage our engineering efforts on the 3D printing and 3D scanning side of the business. Before working at CamLogic, I worked in the enterprise IT field as a system administrator, and before that, I owned my own little company that specialized in custom home theaters, media distribution, and small business IT. So, now that we've got that out of the way, let's go over what we're going to talk about today. So here's the 3 main bullet points that we're going to be covering. So we're going to talk about the available technology in the 3D scanning industry. We're going to talk about the 2 main applications of that technology, which would be reverse engineering and, of course, everybody's favorite, quality control. Before we get too deep into that, though, I want to explain this chart. This is the Gartner hype cycle. This is sort of the life cycle of emerging technologies by Gartner, who is a well-respected technology industry research and analysis company. As you can see, we have on our X and Y axis the expectations of the technology and just the emergence or the continuation of time there on the bottom. We've got this segmented into 5 different phases for the technology: the innovation trigger, which is essentially the invention of the technology, the peak of inflated expectations, the trough of disillusionment, slope of enlightenment, and the plateau of productivity. So as you can see, I've got 3 data points on here, and those 3 data points correspond to consumer 3D printing, which is really at the peak of what people expect can be done with it, and that realization is starting to really hit home that maybe it can't do everything we thought it would, or at least not yet. We have enterprise 3D printing, which has already moved on to the slope of enlightenment, where we're starting to really be able to utilize the technology to move design and production forward. But of course, the one that I really want to draw your attention to is 3D scanning, which is already just about to enter the plateau of productivity. So this is actually the most mature technology out of all these 3, although it doesn't really get all of the headlines maybe that 3D printing gets. And what's nice about that is that once a technology enters the plateau of productivity, it really just sort of becomes a very useful, powerful tool. And I think 3D scanning is well positioned to provide the type of technology that will lead to leaps in other technologies. So let's move on to what's out there as far as technology offerings. There are obviously thousands of different types of scanners that are on the market now, made by all sorts of different companies from all over the world. But all of those scanners really fall into two main technology categories. The first one is laser. So there's laser scanners and there's structured light scanners. Out of all the scanners that you're going to run into, they will fall into one of these types of categories. So let's talk about the differences, pros and cons for each of these two technologies. We're going to start with structured light. So this is a little video that we shot here. This is one of our structured light scanners. As you can see, it's obviously a blue light scanner. Whether it's blue light or white light scanner, it falls into that category of structured light. They all essentially work the same. There's going to be a projector that's actually projecting the light onto the part, and then there will be a camera. Maybe there might be two cameras that are seeing how that pattern that's projected onto the part is deforming. And that deformation of that pattern is how the scanner is actually creating the surface data inside the computer, capturing those 3D points. So this is a look inside the software that runs the scanner. You can see with that we have your typical sort of photography controls. We can control exposure, resolution, image quality, and we just hit test and we'll take a shot, and then we'll get a result over on the right. And obviously, as you can see, the scanner can only scan what it can see. That's why we're missing some data there, and we only really have the side of the part. So what we do is we have to spin the part around to see all of the sides that it wouldn't be able to see in one shot. And then what the software does is it, as you can see there, it actually stitches those two overlapping shots together. So as we move around, as we rotate the part incrementally, we're capturing a little bit of new data and a little bit of overlapping data. And it uses that overlapping data to stitch everything together until we go through the entire 360-degree revolution, and that's how we end up with a full scan of the entire part. So we're going to speed this up here just so you get an idea of the overall process. So you can see we took 10 measurements all the way around the part, and now we have a pretty complete scan of the part. Of course, we didn't catch the bottom because we can't see the bottom, but again, it would be simply a matter of repositioning the part, scanning some new data along with some overlapping data on the bottom and on the sides, and we'd be able to have a very complete scan of the part. So structured light is very good at capturing small things. It can also capture very large things. We have the option of using these positioning targets, as you can see on this sort of one-off roadster that we got to scan. And what it's using here is these positioning targets to register reference points that it will then use to tie the shots together. So instead of using overlapping surface data, you're using these overlapping reference points. And so structured light, very, very clean data, very accurate data, and again, sort of very versatile in being able to scan small parts and large parts effectively. Moving on to laser scanners, they're really not, in theory, that much different than structured light scanners, in that you have a light source, which is of course the laser, and then you have a digital camera that is seeing that light source deform across the surface of whatever you're scanning. The major benefit to laser scanners over structured light scanners is that the laser is such a specific wavelength of light that the digital camera is looking for, we can scan a whole range of surfaces as far as color, surface texture, shininess. They really don't pose much of an issue for a laser scanner. A structured light scanner, on the other hand, would probably need some sort of surface preparation, whether we spray it with sort of a talcum powder spray that lightens up the surface and dulls the surface. The laser scanners typically do not need that sort of surface treatment, so in that regard they're a bit more convenient. Also, laser scanners excel with larger parts. This one, the only thing you can't see in this video is the tracker that's off screen, and that tracker is actually tracking the motion of this handheld scanner while the scanner itself scans the surface data. So the trackers will typically allow you to scan a very, very large part, in some cases almost an entire vehicle with one setup. So it's an incredibly powerful tool. There's the tracker there in the background of this image. And also you have the option of using a hard probe that you can see there on the right, which provides another level of versatility to be able to hard probe certain features if scanning isn't necessary or isn't possible. So let's move on to one of the applications of 3D scanning technology, which is reverse engineering. Some people also like to refer to it as re-engineering. So this is a beautifully restored 1934 Packard 12 coupe. We had a fantastic opportunity to be a part of this restoration. It's not this vehicle exactly, but very similar. And unfortunately, we didn't get to do, the most interesting part of the car. We didn't get to reverse engineer a piston to get the old lump running again, or a headlight or something like that. But we did get to work on the door handle, which, as any car designer will tell you, that it's actually a very important piece of the vehicle, because some refer to it as the handshake of the vehicle. So we still were very excited to be able to be a part of that portion of the restoration. But it wasn't really the entire door handle that we got to work on. It was more just this little door handle mount right there that's highlighted. So obviously, being a 1934 Packard, there aren't any new parts being made, and there really isn't any new old stock available either. So the only real option to get this thing back on the road and looking good is to cast new parts. So this is typically what you would be dealing with. You've got this crusty old part that you need to try and make something beautiful from. So you basically clean it up, you cast a new part from this part, and you hope for the best. So here's the rub, though. When you cast something, you have shrinkage. Obviously, materials moving from liquid state to a solid state shrink, of course with the exception of water. So what happened was this part was cast, and it shrunk, and which wouldn't have been that big of a problem because the door handle and the mount were cast together, so they still fit together. But the mount didn't fit on the car now, because those holes now did not line up with the holes in the door panel. So what we did is we scanned the mount. There you can see the top and the bottom, so we have a pretty complete scan. This was a blue light scanner that we used, so again, very clean, very smooth data. And then we surface wrap it. So we use a NURB surface, just four-sided freeform patches that we wrap the scan data with. So these are actually CAD surfaces, and they're great for freeform shapes like this. But of course, we filled in all of the holes and some of the features on the back because we actually have the ability to perform parametric modeling along with the NURB surface modeling. So of course, we start with our 2D sketches that we use to then create solid parametric features that we can then use in our Boolean operations to either subtract or join or union together. And now we have a very accurate representation of the original part. But of course, we don't want the original part, right? Because we know the original part is going to shrink. So now that we have this beautiful CAD data, we can increase the CAD data by whatever the shrinkage factor is for the material when it gets cast, and then we 3D print it. And then, so this is right off of the 3D printer. You can see it's still encased in the wax. There's a black plastic piece that's in there, and all we do is melt the wax away in a oven, and we're left with a beautiful part that's ready for casting. And of course, then when it shrinks up, it will shrink back to the size that it should. So that's just a quick overview of one example of reverse engineering. Let's move on to, like I said, everybody's favorite, quality control. The inspection department. My theory is you want to fail as early as possible. Failure is not something that we as engineers like to talk about, but we have to come to grips with the fact that it does happen. And of course, the sooner that we can identify a failure and correct it, the better off we are, because it's cheaper and we run into a lot less headaches further down the road. So I'm really talking about specifically really is first article inspection. Of course, we all know that inspection now is sort of traditionally done with the CMM. They are very, very accurate, but of course they have quite a few limitations. One of them being that you have to bring the part to the CMM, which in some cases might not be a big deal, but if you have very large parts, then you have to have a very large CMM. Also, the output from a CMM is just point data, right? X, Y, Z coordinates. So when you get a CMM report, it can be a bit challenging to make heads or tails of something like this, at least in my opinion. I get a little bit cross-eyed when I have to look at these. So I would much rather look at an inspection report that looks like this. You've got your actual dimensions right there on the 3D view of the part, and of course you have what we call our weather map, which will colorize the surface data showing you whether the surfaces are high or low or within tolerance. So let's take a quick look at how we got this report, because I think this is a very good illustration of the power of 3D scanning. Oops. So of course the first thing we need to bring in is our CAD data. That's our nominal data. That's the perfect part. We can bring in just a standard step file. IGES file. We can bring in native files as well from SolidWorks or NX or Solid Edge, pretty much just about anything. And then we're going to bring in the STL from our scanner. As I mentioned, most scanners will capture point clouds, and then you would typically process them into an STL. It just makes the downstream operations that much easier. Of course, we have to do a quick auto alignment because the scan data will not be in the same coordinate system as the CAD data, so we do a quick best fit alignment here so that we can create what we call correspondence. In other words, the software is starting to recognize that this face of the CAD corresponds to this face in the scan data, and from there we can start telling it what the datums are, A, B, and C, and how we would like to align the scan data to the CAD based on the GD&T of the prints. So next we're going to do what we call whole deviation, and that's going to give us that color map that everyone really likes to see. It gives you a really good overview, sort of a general idea of what's going on with the part. What, again, those warmer colors, the yellows and oranges and reds, show that the scan data is sitting above the CAD data. The cooler colors, the blues, are going to show you that the surface data from the scan is sitting below the CAD. And then, of course, we can really dive in to the GD&T of the part. And the first thing we want to do is define our datums. So we're just going to pull off our A, B, and C there so that we can use those later on in the process. So now that we have our datums defined, we can simply pull a radial dimension. As you can see, we can adjust the tolerances. We can adjust the fitting type. We can decide if we want that to be a radial dimension or a diameter dimension. And it's really just as easy as clicking on what type of dimension you want and then clicking on the CAD faces, and the software is going to, again, create that correspondence and create a real-time measurement between what the CAD is, what the nominal dimension is, and what the actual or measured dimension is from the scan data. So we're going to pull a couple more dimensions off here. I'll do some linear dimensions. Again, adjusting the tolerance, and you can see there that that dimension shows up yellow, which means that we've used up more than half of the allowable tolerance, but the measurement is still within tolerance. That can, of course, be adjusted. You can keep that green if you like. Again, we can replicate just about any GD&T callout that you'll find on a set of prints. There's a true position callout. We can put in material conditions if we like. Put in one or two more. And again, even complicated surface profile, so we can take this entire perimeter profile and take a measurement on that just as easily as selecting all the CAD faces and then deciding where we want to put the call out. Of course, the whole reason typically that we would run an inspection is to get the inspection report. So here's the inspection report that you get when you have data from a 3D scanner versus the CMM report that many of us, I'm sure, are familiar with. Again, I would much rather be flipping through this report, looking at these pictures. Humans, of course, are visual creatures, so our brains tend to understand this type of information much better than we do just a spreadsheet full of numbers. And it's really just as useful, and really, I think, sinks in and hits home much better than a CMM report. So that's just a quick overview of how our inspection workflow happens here at CamLogic. But of course, you know, with all of this fantastic technology and all of this power, I really would be remiss if I didn't bring up our old friend, the calipers. I don't know a single engineer or designer that doesn't have a set of these at their desk. They are indispensable. Some of you might be spoiled. Maybe you've got the 8-inch version. Mine, I've only got the 6-inch variety, but I manage quite well. I think it's an indispensable tool. It'll probably never be replaced. They're reliable, they're cheap, they're readily available, but I do think that these will be supplemented with 3D scanners, probably in every engineering department that you come across. I think it's going to happen on a large scale, and I think that many of you are probably thinking, but 3D scanners are really expensive, so how is that going to happen? Well, I don't think it's that crazy of an idea to think that you'll have your set of calipers right alongside a desktop 3D scanner in the relatively near future. So let me try and explain why I think that's true. So they're super portable and easy to set up, and they're great to perform first article inspections and revamp designs. What you're already seeing is apps in all the app stores for all of your mobile devices that are actually already capable of 3D scanning. Again, of course, they're not going to be metrology grade. It's sort of a novel thing at the moment, but it's free. I mean, that's pretty powerful, I think. You can get one step up and go to a dedicated 3D scanner, a handheld scanner for just a few $100, and then you can step up to more professional quality, or at least really high-end hobby quality scanner for maybe $1,200 or $1,500. After that, you're talking about a decent structured light system for the neighborhood of 10 grand, maybe 20 grand. And then, of course, you've got the high-end systems like the laser system that we saw earlier that's going to be up around 100 grand. So you've got a whole range of products available at a huge range of prices. So that's all well and good. I don't see, you might be saying, I don't see us buying a $100,000 scanner anytime soon, and the one on my phone isn't really that useful. And I understand that, but what you have to remember is there's a few things that happen with this hype cycle. As time progresses, not only does the technology mature, it also becomes cheaper. So I want to share with you a few technologies that were sitting right at this very point where the 3D scanning point is sitting right now. So just a few years ago, mobile app stores were sitting right at that point. E-paper displays, the display that is on your Kindle reader that costs, I think, $70 now. Biometric authentication was sitting right where 3D scanning is sitting now. That's the home button on all of the new iPhones. So it's all built into the technology that we use every day. Even speech recognition was sitting at this point on the Gartner hype cycle not that long ago. So Siri, Google Now, Cortana, that's all just ingrained in our lives, and it just happens automatically, and it's nothing that we think too much about. So I don't think that it's that much of a stretch to think that 3D scanning is going to just become a normal, everyday, fantastic tool for us engineers and designers to use going forward. So thank you so much for your time today. I hope you've enjoyed it, and please